the goal of this paper is really to come up with some sort of guarantees on efficient auditing. So the way I like to start this talk is imagine you are having a friendly conversation like this one in some cafe, and all of a sudden someone asks you a question. What is going to happen to AI in the future? Um, and you tell them, well, of course, AI is amazing. AI defeats doctors at diagnosing illness. And in fact, it's only going to get better. Uh, we're we're increasing our capabilities every day, and so in the end, we're all dead. Um, and well, this is slightly humorous, but maybe if you don't believe that we're dead, you might even say that things are already quite bad with language models, as you all are quite well aware. And so soon a friendly conversation turns into a very silent conversation. So what can we do about this? Well, there is a very famous paper in 2021 called Unsolved Problems in ML Safety by Hendricks et al. And they argue that there are really four categories of problems that need to be solved. Um, the first one is to create models resistant to adversaries, unusual situations. The next one, the third one, is also to create models um, that specify human values. And the fourth one is also to create models that address how machine learning is handled. And the issue with these solutions is that, well, only massive companies can create the models that are the ones that are inducing these safety issues that we care about. And in fact, if you look at the authors of this paper, 3 out of 4 of them were in big AI labs, and I think the last one joined one soon after. Um, the second one um, uh, is different from building models. It's about detecting, monitoring, and discovering model functionality. And so maybe, if the other three, if they're done by big models, maybe we can also leave this to, sorry, big companies. Maybe we could leave this to big companies as well. Um, or maybe that's a bad idea. Um, you all have seen some very interesting prompts. This was when like GPT 4.0 was released, and we got some responses that were quite complimentary, maybe over the top. When GPT-5 came out, someone had an idea of testing its kind of reasoning abilities, imagining a rotated tic-tac-toe game. And GPT-5 is very happy to describe this game, invent it, and even draw it. Um, and creates this game with quite interest, despite the fact that the game does not change if you rotate the board. So this is really the motivation for this talk. Maybe monitoring should be done by organizations that aren't the companies developing, or at least alongside the companies developing these models. And the question is, how can we do this efficiently and reliably in an external fashion? So because we are external to the model, all we can see at any time, sometime t, is a prompt that we give the model and its generation. So the prompt is x and its generation is mx. And then we can look at a later time. M prime, maybe the model has changed. And we can give it the same prompt and see what the change looks like. And we might want to know over time if the model is changing in a meaningful way. so that we could flag it. But we don't care if the outputs are exactly the same, right? You could have a rewording of an output and it could be meaningfully the same. All we really care about is if the behavior of the model over time is similar, is sort of well behaved. Um, so what we can think about is we can leverage a large body of work on behavior functions. People have been designing behavior functions even before large language models, things to measure the toxicity of a text, the whether it has bias, and then things that are starting to look at large language models in particular, like hallucinations and situational awareness, nearly every behavior you can think of. Um, so if we're an external company that wants to audit language model over time to make sure that its behavior isn't wildly changing in some unpredictable way, well, what could we do? Well, naively, what we could do is we could pass a bunch of prompts, get its generations, and then compute the behavior function of these generations. And we could do that at one time point, and then we could do it again at another time point, and we could compare these behaviors. But this naive way is not so nice because these evaluations are, in order to assess behavior of a model, they're massive, right? So if you go to Google's developer page, they have more, more than three benchmarks to just evaluate toxicity. And only one of them is 100,000 sentences, and the other two are large scale or have a description that says large number. Um, and there's even more than these. So if we were an auditor and we were required for every behavior to run this large scale audit, this would extremely limit the amount we could do this. And we would kind of have to be quite selective about which behaviors we cared about and forget other ones. So this isn't very satisfactory. So in our paper, what we asked is, can we do this in a different way? Can we have some original set of evaluations in order to characterize a behavior distribution in some way? And then when we go to test the model again at a future time, we test one of those prompts and we get a generation, we compute the behavior, and then we ask, are these models' behaviors similar? And then, okay, we might not know just from one prompt in one generation. So we do it again. Another prompt, another generation, another behavior, and then we ask the same question. Are they similar? And hopefully we we only have to ask this a very small number of times, and come up with a guarantee that the behaviors have meaningfully changed if they have, or control on the false positive rate if they haven't. So the way we decided to frame this was to think about these not as a bunch of observations of behavior, but as samples from behavior distributions. So we have a bunch of samples initially from the first time point, and we have a future time point, or possibly many future time points, where we're trying to sample, we get samples of behavior of that model potentially changed. And the question we're trying to formalize, the way we formalize our question is, we want the distance or the divergence between these distributions to be less than or equal to epsilon. So, we have some certification from the initial large scale evaluation that the behavior is fine. The distribution of the behavior is acceptable. And we want to make sure over time that this behavior stays that way. Um, so if we frame it in this way, we can leverage really exciting recent advances in sequential hypothesis testing. This is a really actually fast growing field. There's been a lot of really cool developments on martingale theory. Um, and I'm going to describe a generic approach, which allows you to plug in your favorite, basically, sequential hypothesis testing approach. We use one in the paper that's quite recent, but it's really whatever you want. And what we're going to be testing is the null hypothesis that the distributions haven't changed, that their divergence is less than or equal to epsilon, against the alternative, which is that the divergence is greater than epsilon. Okay, so how would this algorithm work? Well, what we do is we have this initial time point where we compute all these behavior scores and we're satisfied with that behavior distribution from those scores. And again, these are just prompts and generations. This is just API calls, and you have some behavior function you care about. Then time passes and you're curious, okay, has the model behavior changed in an important way? Like, if I tell it to rotate tic-tac-toe, will it find that an interesting game? So what we do is we select a prompt, one out of the ones that we've evaluated initially, and we compute the behavior score for that prompt. And then we use that behavior to update a test statistic. And there are specific details for every sequential hypothesis testing method, but suffice it, all we really need to know is that there's a test statistic that if it grows large enough, we can reject the null hypothesis. And alpha gets to control that threshold, which is the acceptable false positive rate, for instance, 0.05. So you get a larger threshold if you have fewer false positives and smaller one if you have you're okay with more false positives. And if you can't reject the null, if you're not above this threshold, you repeat, you go back to step 2. So we developed a approach. There's been a lot of work on exact sequential hypothesis testing, but we generalized this to this epsilon ball testing. And what we were able to show is that under certain, actually not difficult to establish conditions, not hard to satisfy, the test has the following guarantees. The first guarantee is that under the null hypothesis, the probability that the test stops is less than or equal to alpha. So this is our guarantee on the false positive rate. Asymptotically, we will have a false positive rate of, at most, alpha. And for the alternative, asymptotically, if the alternative is true, we will detect it. So these are the guarantees we wanted, but they're asymptotic guarantees. And it's quite difficult to have finite sample guarantees in the setting we're considering. There's actually only very recent work on this. So the natural question is like, okay, Matt, like you gave us some nice guarantees, but maybe they never actually happen. Maybe they never hold. So now I need to show you an experiment. So what we did to test this is we took Llama 3 8B instruct. This is a bit of an old model, but we were doing these experiments in 2024, so it's a bit outdated, bear with me. So these models, we take a base model, sorry, an instruction tune model, and we further instruction tune it on different tasks in super NI. This is like a natural language understanding benchmark. And we compute the toxicity of the model after instruction tuning. And we have this perspective API for measuring toxicity, and we have certain prompts called real toxicity prompts that we will use to test this. And what we do at the beginning is we just look at, okay, for different amounts of instruction tuning, these colored models, how does it compare to um, a model that only differs by like sampling variation from the base model? Um, and we can also compare it to an uncensored version of llama. This is just to set up the experiment, by the way. Um, so what we can also measure like a sort of distance between the models as well. So what we imagine is we have an allowed epsilon difference of 0.0038. And why do we pick this? Well, we pick, so this is the distance in terms of the bottom line. So at this threshold, any change in toxicity that is due to instruction tuning or uncensoring um, should be is above the threshold, and so it should be caught. So what we're testing is how fast can our approach catch these models that have increased in toxicity at this threshold. Hopefully not with infinite samples. Let's see. So we I'm going to show you a graph where on the y-axis is the proportion of tests that were triggered over, I think we ran the test 20 times, I think, for each model. And on the x-axis, the number of samples it took for each proportion of triggered tests. These are the different instruction tune models, the specific data sets, as well as an uncensored model. And so here's what the results look like. So what we can see is that for 1,000 samples, that for nearly all of the curves except gender classification, common sense classification, and translation, 95% of the tests get triggered at 1,000 samples, whereas it takes about I believe we ended at 1,900 samples, and we can get 95% of tests triggered for all of the fine-tuned models. So this is much lower than running an entire evaluation of 100,000 prompts, for instance. But we also need to make sure that we're not triggering models that are we're not getting our false positive rate too high as well. And so the way we do this is slightly differently. So on the x-axis now, instead of number of samples, we are picking the epsilon that we're selecting for our test. So we use different ones for different data sets because this corresponds to that earlier plot I showed you of that distance line. So like once epsilon if epsilon, is below the slightly above that distance threshold, then the model change shouldn't trigger, and as soon as it gets below that threshold, it should trigger. So I'm going to show you curves like this. So let me go through a line, for instance, this purple one. So at the below this threshold, we see that tests are triggered, which is what we want to see. There's some difference in these models, but as soon as we have a test epsilon above, and actually even slightly before, um, we see that the proportion of triggered tests go to zero. And this seems to happen for all of them except for this pesky orange data set. Um, and we think this is basically due to sampling error. Like if we were to run this enough times, this should go down to zero. But I think we just don't have the right number of trials. So this gives you a sense of like, as long as the threshold gets large enough, then the false positives converge to zero. I can also show you a little bit like an easier to understand test. So an easier to understand test is if we just set epsilon to zero and we say we don't accept any sort of change at all. And what we do this time is we fine tune the model to be more and more toxic slightly. So this is easier. And what we hope is we would require even fewer samples for this. So I'll show you this again, where I'm looking at proportion of triggered tests on the y-axis and samples on the x-axis. Of course, higher is better. And what we see is that, this time, in order to get 95% of tests to trigger, for all models except the very close model, we only need 500 samples. For the very close model, it seems like you'll need much, much more. But that's because, the true, so on the right, these are like the true epsilon, which are all greater than zero. But this initial one is quite close to zero. So depending on how close you are to epsilon, you will need more samples. So we did this for Llama 8D Instruct, and we tried some other language models as well. We did this for Gemma. Again, these are a little bit old, these models. But we also did this for Mistral as well. And all of these took less than 500 or equal to 500 samples to have 95% of tests triggered. And then we can also look at false positives by samples. This is different from the earlier false positive plot because now I'm showing how many samples on the x-axis. And for all of these, where our false positive rate, the way we test this experiment is we just test it against itself, like a different version, sampling from itself a different time. And we can see that even though there are some tests that are triggered, overall, the proportion of tests is still below false positive rate, which is what we're hoping for. So I've hopefully convinced you that this approach in some settings can seem to be practical, but there are still some important limitations that I want to flag about the work, which is that this approach is not suited to catch backdoors, right? So backdoors are, tiny adjustments, imperceptible adjustments in some very remote region of the distribution. And technically there would be a change in the distribution, but likely the number of samples you would need to detect this would just be massive. There may be a way to use sequential hypothesis testing to catch backdoors, but you'd somehow need to find a transformation of your distribution that would highlight the change in behavior caused by backdoors, and you'd also you need to be very clever about prompt selection. So we didn't cover that. I think we're also importantly missing finite sample guarantees. There's some recent work out of Aditya Ramdas's group that describes finite sample guarantees, but this is like at the cutting edge of the theory at the moment. And the last one is that we just randomly select prompts. it's probably going to help a lot if we could select prompts in a way, in an adaptive way, so that like, we were like covering the distribution in a more clever way than random selection. So that's definitely something I think that could improve the sample size that would be necessary. And that's all that I wanted to tell you today. What I wanted you to take away from this is that I think there's a real need in the future for independent evaluations. Um, but in order for these evaluations to be frequent, widespread, um, this has to be a scalable process. So our idea was to frame this problem as a sequential hypothesis testing problem, which allows us to leverage and adapt, modify recent work in sequential hypothesis testing to derive guarantees on the false positive rate, as well as the consistency of the model. And uh, the approach, we were able to show that it catches model changes in under 2,000 prompts, and in some cases, much fewer than 2,000 prompts for the models we tested. It would be really exciting to see more work on this on more recent models and more recent data sets. So that's all I wanted to say. Thank you all for coming to this. I'll take any questions you have now, and this is also the paper and the code if you're interested in this.
Yes, thank you very much, Matt. It was very interesting and like a very lively presentation, and it is very nice that we have a lot of time to have questions, because I think that at least from my side, I have quite a few questions, but I think that I'm gonna leave the first question to the people in the chat. And there was someone asked, how do you assign values to behaviors objectively, like toxicity and bias? And different groups of populations might assign different values to behavior. So this is back in your slides when you were presenting the curves of, with the increasing sample size.
Yes. So are you talking about maybe here or?
Yeah, I think it was in here. Yeah.
Yeah. Yeah, so this is a good question. Yeah, so these behavior functions, they they're very they're nebulous. So it's not like early behavior functions. We're looking at individual like word usage or like unigrams or bigrams, trigrams. Um, and more, these evaluation functions have come to be themselves language models. So you send the prompt, and the whole entire role of the evaluation language model is to say like, oh, how toxic is this? And it's not very um, it's not very obvious this is the right thing to do. Um, I I don't see a way to get around if we are trying to come up with some automated way for auditing. I don't see a way around using behavior functions in some way, because we need some. It feels like for automation we need some quantitative way to measure the like what we don't like about the model. Um, but I think it's a reasonable it's reasonable to question this, and reasonable to ask if we want all of the process of uh, language model evaluation to be automated. I think there's strong arguments that we don't for having aspects of automation that aren't automated as well. Although that also comes with challenges such as data workers who have to deal with like very toxic outputs from the model, or images generated. So there are costs there as well, but it's a very good point. The behavior function is something that's abstracting a lot of the difficulty away from this problem.
Yeah, absolutely. So I have a question on this, I mean, on your answer. So if if the behavior function is itself an LLM,
Yeah.
what you're saying, I mean, from what I understand, is that the question then becomes what happens if the auditor model drifts or has its own biases, right?
Yeah.
So,
Yeah.
like, do we risk some sort of recursive auditing loop?
Hmm. Hmm. Yeah, it
Yeah,
seems like it. So
yeah. So, hi, this is okay. This was my question. So again, you framed it very nicely. So I was just thinking, if AI is being used for this behavior assignments, could it be resulted in the positive and negative feedback loops and render all the results on behavior, valueless, except you can only detect the change, that something is changing, but can you say with some confidence whether change is in the right direction or not because
yes.
of this feedback loop?
Yeah, very good question. Yeah, yeah. I yeah, this notion of bias in the auditor and feedback loops, I think these are these are very good concerns. Like, they're one very popular approach. Yeah, so the approach of using language models for behavior auditing is this idea of LLM as judge. And I have so my student has a paper recently about um, agents, which are different from LLMs, but there's some relationships. How if you ask them to do certain tasks and you ask them to evaluate how confident they are at the solution to the tasks, they're way overconfident. And the same goes actually. There's prior work that looks at this for language models themselves. They're way overconfident in their responses. So yeah, I think we've so we've so there is also an additional work on um, uh, language models that are evaluating other language models, and if they come from the same like model family, they tend to be like give much more favorable responses to the same model family than like to different model like Claude Anthropic models more favorable to Anthropic models, less favorable to like OpenAI models. Uh, so I think yeah, there's like these are, I think, very strong arguments against automated evaluation. It seems like the only solution that I can think of to these problems is not a technical one. It's just using humans in the loop. And I I would I would be completely happy with this. I will not defend using language models to evaluate other language models at the end of the day, because I don't. It seems like there isn't, as long as language models hallucinate, as long as uh, there are unaddressed like safety issues, uh, I don't see a way around this.
So, so I don't want to drag this discussion. So my last question and comment here. So I understand what you say and your challenges here. I was just wondering, for example, like if we take the insights from how human populations behave with the collective effort. So human, every species has a kind of like a survival instinct. So they wants to collectively, if you ask 100 a group of people, they will collectively agree on the things that are best for survival. So my insight and question here is, can we use multiple models from different companies and groups together
Mhm.
to evaluate behaviors so that it becomes like a mixed population and their bias and toxicity should reduce if they tend towards the survival.
Yeah, uh,
So
that's a good.
using the multiple models to pitch against the behavior toxicity rather than having one model and just one model to evaluate to avoid the feedback loop?
Yeah, yeah. I mean, there's like this notion of like also of ensembling in machine learning in the theoretical literature of machine learning as well. And these are the models that are usually ensembles of very different models are the ones that are often winning the Kaggle competitions. So yeah, and there's you can derive guarantees for ensembles on reducing bias, like in the classical sense of estimation bias. Um, so it it seems correct that you could get a you could reduce some sort of estimation bias in that way. Although I don't like it's not obvious to me that this would reduce sort of like kind of other kind of like toxicity just because it's not the way models are trained. It's just as sort of like predicting the next token, next token, next token. I don't see an easy way to sort of guarantee that this ensemble of approaches would reduce overall toxicity, for instance. It might like you might have a more sort of accurate generation in some estimation sense, but I don't see it being less toxic because it's reproducing the data it sees, which is often toxic.
Mm-hmm. Okay, let's park this here and move forward.
Okay.
Thank you very much for your insights. Yeah, it was
happy to discuss it further offline as well.
Yeah. I have a question before we pass. There's another question in the chat. I just wanted to ask a question. So say I'm a company that wants to implement this. So as I see it, the inclusion of this configurable tolerance parameter epsilon is like a major practical strength in your work. So how should my organization determine a correct epsilon value in the sense of is there a methodology to map between something that would look like a business requirement, say zero tolerance for toxicity, even if it's never like you can never ask that as a requirement, you will never get it, but mapping something like that looks like a business requirement to a specific statistical epsilon?
Oh, yeah. So we tried to in the paper. I didn't go into this, but this is a good question. Yeah, we tried to imagine if you were like an internal team that needed to come up with an epsilon of imagining so it really depends on the quantity, but like let's say you were looking at some sort of like hallucination behavior. What you might want to do is you might want to change a model in ways that would simulate the kind of fine-tuning changes that you might do naturally over time. And then try to measure using, I didn't get into this either, there's a distance that is between model outputs, between model behaviors that defines this epsilon. So what you could do is you could, okay, I could imagine I want to fine tune this model in this way over time. I want to fine tune this. It's going to be hard to simulate this completely, but you end up with a series of changed models, and you measure this distance, which corresponds to epsilon between each of those, and then you try to use that to calibrate the kind of changes you can do a full evaluation of each of these models to make sure nothing has changed. And then
I see. So what you're saying is like you're actually so it is actually you're answering in a different way that I expected, but it's a very nice answer. What you're saying is that you can essentially say that the value of epsilon could be used to determine what are valid modifications of your initial model, so that it gives you a span of allowable modifications that would still fall into the same epsilon value. Okay, I see.
Exactly. And at some point, maybe there's some important category shift or something, and that's when you define sort of the epsilon that would divide those two shift, like the less change from the larger change.
And I think last comment is important here. For example, the category, because epsilon, I think statistically and looking at the language models, zero epsilon is not a possibility, as I think, because if you look at the wider point of view, they are already in our knowledge base as a human or collective knowledge on this. These models are trained on, there is no agreement. So when there is no agreement behind the scenes on the knowledge where the LLMs have drive the conclusion, you cannot reach zero epsilon, because there is a conflicting training where the models are trained on. But if you categorize, you have to create a subset of your parameters, and only in those subsets you have the variability of epsilon. Because, for example, there are some ethical and moral questions where there is no settled answers. And how can you say there is kind of like no bias? That means zero bias will not give you any new insight except being the politically correct or maybe the neutral.
Right. Well, yeah, and I will say it also depends on sort of the way you evaluate behavior as well. Like what the behavior you define to be some sort of acceptable range of your behavior distribution. And then yeah, as you say, like inadvertent fine-tuning changes might have an impact on that behavior. But it might not sort of like quantitatively change it in a meaningful way. So like your epsilon hopefully captures that sense.
Yeah, absolutely. So essentially, if there is a methodological mapping, it would go from the epsilon to the some allowable span of basis requirements that I mean, more like a specification of what to what extent the system can evolve and guarantee something. There are two questions in the chat. I had another question about this about your last point on the metrics, but I
Okay.
prefer to. There are two questions. First from Busad. Maybe you wanna say it out loud, or do you want me to?
It's okay if you want to to ask it.
Yeah, go on. No, go on, please.
Okay. Yeah, I had a question. What about using an embedding model to calculate the similarities between the responses of your different models?
Yeah, okay. Right. So what you do is you look at the generations, then you embed them in some space, and then you say, okay, if the embeddings are different in some sense, then the behavior is different. Yeah, I think that would be like to me, the way I think of this is that could be a way to construct some sort of behavior function. Like if you found some meaningful type of transformation that allowed you to and like if models generations really look different, then their embeddings correspondingly were different, then absolutely, I feel like that could be like in like a very broad sense, this behavior function. The reason we need it is because we can't actually we can't efficiently test the sort of the distributions of generations. We need some dimensionality reduction in order to compare in a like a small enough number of samples the how changes happened, because you know, the space of generation is just so large. There's like, and in some sense there are some directions in that space you don't really care about, like summarization or something like this. So yeah, I think using that approach could be a reasonable.
Actually, I'm asking the question because basically embedding models are built for exactly this task to make similar text get similar vectors in an hyperspace. So if you calculate the similarity between the different responses, you can you can measure if there is some shift in the behavior of your model.
Yeah, so maybe that's a good a better way, instead of using language models, to come up with an automated behavior function using some type of embedding model.
Yeah, definitely, and obviously embedding models are much faster because they are much smaller than LLMs. Thank you.
Yeah, thank you. That's an interesting point.
Okay, we have another question from Ivan Roland. Maybe you wanna ask it, since I say that it is a development and a question too. Ivan, are you with us?
Yes, sorry, I have a problem on the LAN. I don't hear your question. Sorry.
No, my point. You asked a question in the chat. I thought you wanted to ask it.
Yes.
Live. Yeah.
Yeah. I put a little text to more understand what I'm saying. It is that today we have a lot of model, commercial model, etc. But for me, it's my opinion. I don't know if it is, and it is my question. Today we are starting with model who are trained to understand and to exchange between chat to answer some question. But in fact, they have been trained at the beginning from data from the web, from books, etc. So in each time there is a bias, because if we took all the book we have in the humanity, there is still bias coming from the human people. So my question is, today, do you know if there is some monitoring concerning the bias introduced by, I don't know, a certain percentage of book used to train a model, for example, religion, political subject, etc., on how it is, how can I say, vectorized, in fact, in the model, to explain what's happened, because for me it is a black box, like we don't. I don't know if we are able to monitor or to understand what is the impact, in fact, of the training.
Yeah, there's very to my knowledge, I'm not an expert, but to my knowledge, there's very little work on like training data attribution for outputs. I think the work that I know about, there's what you can do is you can start from a generation, and you can back propagate all the way to like embedding vectors, and then try to do a matching between the inputs that you have and those embedding vectors to see which inputs sort of correspond most closely to the embeddings that led to a particular output. So I think there's a little bit of work on that, but it's not. I think it's a very not well understood area.
And is there any research that can distinguish the content, I mean, text content I'm talking about, not the mathematical or scientific, for example, text content generated by humans and generated by AI models? Where I'm going with this question is that, for example, state actors, and if I want to bias all the models that are using the data discovering or from the internet and train themselves, if
Yeah.
I'm a state-sponsored actor and I use AI to generate content that seems reliable and genuine enough, and other models start consuming it, I can bias a wide body of LLMs that rely on the data from internet. So
Yeah.
what is the research body that is working on to somehow possibility of identifying or flagging the text data generated by AIs and the human produced text?
Good question. Yeah. So I know there are tools out there that try to identify LM generated text. I'm concerned about this too because I'm working on a conference for UAI, and we're trying to detect whether papers were completely generated or whether they have like um, text in there that's hidden that can influence like LLM-based reviews. So yeah, it's a really important question. So a few years ago, a proposal I really liked was to try to watermark generated text. And the way the approach worked is you you basically the simplest version is you just have a set of words that you decide that the language model can basically can never say. Um, and you call that like a red list of words. And like this red list, ideally, like you pick this in such a way such that there are like synonyms that so like you can still accurately describe things. You just never describe them in this using those words. Um, and then what you do is you can come up with a hypothesis test for any text uh, uh, based on this. So like you might have a set of text that like would never use those words in any case, but you can still based on like sort of the likelihood of coming up with these sorts of words, identify whether it seems to be coming from a language model or not. As far as I know, like language model companies have not adopted this watermarking, but that seems very promising. At the moment, all of the tools that I know of that try to identify a language model text just train on generated text from language models and then try to discover it. But this is problematic because, of course, language model texts are reproducing or kind of mixing human texts. So I don't think they're very accurate at the moment. I think this is another very interesting open question.
Yeah, sorry to interrupt because the conversation is very important, and there was some other questions in the chat, but it is time is up, and we still have another talk, so I will have to sadly propose to everyone to contact Matt for further questions, and indeed, watermarking poses another category of questions in itself. Anyways, I wanted to warmly thank you again, Matt, for this talk, and hope to see you soon in some other format.